Does anybody know what this device is called? Right? We're measuring the mass of these particles. It's similar to a cathode ray tube. A cathode ray tube, it will deflect it to make pictures, basically, right? This is a little bit different because the cathode ray tube does not have this external magnetic field, but they're very similar. This is called a mass spectrometer. I'm sure you all heard it before, but you probably thought it was very complicated, how it works. The fundamental principles behind it are very simple. It's just this magnetic field that we could select particles at a certain velocity and send it into another, an external magnetic field, and it'll rotate with some rate, it'll cause circular motion with some radius r that depends on its mass. So this means that we can measure mass of very small atomic particles. And we could study now the properties of these particles easily, right? Of course, in real life, the sensitivity of these machines are very precise, and it's very difficult to make these measurements because of external fields. You have to take that into consideration, and the uniformity of these magnetic fields as well. There's a lot of small nuances to it, but the basic idea is pretty simple. So this is a mass spectrometer. Now, I could go into a cathode ray tube very quickly. I'm pretty sure I did it in the previous lectures. And now I kind of got ahead of myself here. So before I go into a cathode ray tube, I'll probably do it next time. There's some more material that I want to cover that's basic, pretty basic. So. So the next thing that I want to talk about is how can we use this magnetic, the forces on this magnetic, due to a magnetic field, use it for practical purposes. Now, as you've seen, this force is perpendicular to the motion, right, of the charged particle, and you can create the circular motion pretty easily because the force is always perpendicular. So why don't we use this to our benefit, right? Now, let's say I have a loop of wire. I make a loop of wire, single loop, like that, right? And I put it on a spindle so that it can rotate freely. Right? Now I send in a magnetic field. I have a magnetic field in this direction. Right? What are the forces on it? Let's figure it out. So let's consider the four sides. 1, 2, 3, 4. So which direction is side 1 pointing? Everybody, that's what about AFM? And AFM, atomic force microscope? Oh, that actually works a bit differently. So it does use a force. It does use van der Waals forces, which is electromagnetic force. Well, what happens? It's quite interesting. I'm actually building a setup right now on it. So what happens is that you get this cantilever, right? And it has a tip on it, right? And think of this cantilever like a diving board, right? The diving board is like a spring moving up and down, right? And if I attach another piece to this diving board, it moves up and down at a certain frequency, right? It's resonant frequency. When I bring it close to the surface of something, that's hard to say. When I bring it to the close to the surface of something, I change this resonant frequency because of the forces that this probe feels on the surface. And you could detect the change in frequency, and then you could detect the height at an atomic scale, which is pretty incredible. So that's very different from this, but it's also very cool. It's cool that it physically moves, and then you're detecting the physical movement of the tip. It's pretty amazing piece of machinery. Yeah, no problem. So back to the forces. So on side one, let's draw the current. So the current comes in this way and leaves that way, right? So it's going up here, across here, down here. So the current is this way. Everybody, let's do the right-hand rule. The current is upward over here. Force is that. The magnetic field is that way. Force is into the page. So the force is into the page, right? What about on the top? Let's do the same thing. Everybody do with me. I can't ask for the answer, really. It's difficult. So force that way. The magnetic field is the same direction. So where would the force be for this top particle? For this top wire. If the force and the current are in the same direction, what does that mean? If the magnetic field and the current are in the same direction, what does that mean about the force? Anybody? So let's look at it. If you can intuitively think of it, let's go back to your equations, right? So we have the cross product of the current. I'm not going to write L. Well, we could do L times B. And then the magnitude is equal to B, right? And then right now, the current and the B field are in the same direction. So what does that mean for the force? Right? So this is the current. And then the B field is along the same direction. Sine of 0 is 0, right? And if you think about it, this makes sense, right? Because you can't define a vector, a single vector perpendicular to one line, right? So both the magnetic field and the current along the same direction, any vector in this that's circling around here is perpendicular to both. Once you introduce a small angle, right? Once you introduce a small angle, this is no longer the case. The only vectors that are perpendicular to both of these right now is out of the page or into the page. And again, over here, when it's 0, there's an infinite number of vectors that are perpendicular, right? It's just radially outward from this line, right? You can rotate it around here because these two vectors actually make a plane. You can define only one or two vectors, one going up and one going down, right? And then we figure out whether it's positive or negative by the right-hand rule. And then if you use your left hand, it would be in the opposite direction, of course. So in this case, if the current and the magnetic field are along the same direction, this force is 0. Over here, it's moving downward. We can use the same logic as this side, and we can say that the force is into the page. Everybody, let's confirm that. So this is a little awkward for me. I'm sorry, out of the page. So the current is going downward, the B field is that way, and you can see my thumb, it's pointing towards the camera. So this is going out of the page, and then on the bottom, the force is 0. Okay. Now if you look, this force is the force is pushing this part of the wire inward. This is pushing outward, right? If we just do a top-down picture of it, right? This is the spindle, and then you got your two wires, right? That one's coming towards us. The current is going down over here. The current is coming up here. The forces will look like this, right? Force 1, force 2. Right? Now, what will happen to this wire? Can anybody tell me? If we have if this is on a spindle, we have a force going this way and a force going that way, it will rotate. That's correct, right? And we will get rotation along the axis, and we'll spin the spindle. This is a device to convert electrical energy from the current into motion, right? This is a motor. This is how all electric motors work, right? It's really cool. It's super simple, right? It's not complicated. Of course, to make the force large enough to move a car like a Tesla to 60 miles an hour in under 3 seconds, you need to design these prop loads to increase the force and very efficiently. And these can be very efficient, right? So let's figure out what kind of forces are on this, right? So we no longer really talk about forces, but we need to talk about torques now, right? So if you remember, I think I went over it in lecture. The force is, right, it's times the lever arm. Because the force is always perpendicular to the lever arm, you just multiply it, right? So let's define the lengths of this structure, up and down. This is A, and then across we'll call B, right? And we need both because A represents this L over here, and B is the lever, or half of B is the lever arm. So let's figure out the two torques. We know that we only have 2 torques, right? So the torque is equal to the lever arm, right, times R. And of course, there's that sine theta, and then that sine theta is 90 degrees because this lever arm and the force is that way, right? And then this is also a cross product, remember, right? The torque is the cross product between the force and R. But we don't really need to worry about that right now. So then the torque becomes, right? It becomes torque 1 plus torque 2, or torque, I should say, sorry, torque 3 to keep it accurate, right? And this is equal to the force times R. If we look at the torque, it's just this. Sine theta is 90 degrees. I should write sine theta prime over here. This is because this is a different angle technically. So then it becomes I times A. A is this L up here, times 1/2 B, right? This is the lever arm. This is equal to 1/2 B, right? Plus the same force, right? And if you look, even though the forces are in opposite directions, because they're 180 degrees from each other from the central axis, they have the same sign for a torque. Oh, I forgot to add this times the magnetic field, of course. And it's the same over here, and it just comes out to be I times AB, and then your final expression, right? A times B is just the area, right? Because this is rectangular. So it comes out to be I times the area of this loop times B. And it actually ends up it doesn't matter whether it's round or the shape of the loop, it's just the area that's in between the loop. Right? That's really cool. We calculated the torque on this just based on the area of this loop, the current, and the B field. That's all. Comes out to be a very beautifully simple equation. Now, what we could do to increase this force is to add more loops, right? If we add another loop, we double the torque, and so on and so forth. So what we could do is just keep wrapping around more loops, right? This is why if you ever seen a motor, right, like on a drill, you see copper coils wrapped around each other, right? This is to accentuate the force, right? So if we have n loops, right? The torque is N times A B, right? Very similar to a solenoid, if you guys did the lab yet. Right? Now, this is the force for one position, right? When it's in this position, right? Now, when it rotates around, Now imagine, so right now we're looking at it in this position. And right now the B field, let me draw the B field so you know how it is. The B field is going through the wire like this. The way I drew it over here, you can't really tell the perspective, but it's at an angle. If you look, I drew it at an angle. But over here, and this orientation, it's going through, the B field is going through here. Now, when we rotate it, right, when it goes into this position, right, and the B field is in the same direction, what is the torque on this, right? The force, of course, is the same, right? The force, you know, if we rotate this up, the force over here would be, how can I do? So now the force is in the same direction, right? The force is upwards, is over here, right? Because the current is going into the page over here, right? This is this section, this is at the top. Oh, I'm sorry, out of the page. And then over here, it's going into the page. So the force is in along the same direction, right? Let me write it like this. So the lever arm we not quite. We won't. We can use it eventually, but not at this moment, because we're just sticking with the torque formula for the moment. We don't really care about its centripetal force, right? We just care about the torque on it, because the centripetal force is being held in place by this spindle and the connected wires. So the centripetal force doesn't really come into play in this problem. We just care about the torque. So right now, when it's rotated and it rotates up to this point, the force is pointing upwards and then downwards, right? It's along the same direction, because the current is always moving out of the page over here and is always moving into the page, right? Because this is a top-down view. And in this position, the lever arm, or this R, is 0, right? It's 0. All right. Now, what happens next? So it goes from this torque and moves up, right? Because it rotates because of this torque. It goes to this position. At this, the torque is 0. And then it rotates to the other side. Now, once it rotates to the other side, right? Once it rotates to the other side, let me draw it. So we'll move from this, and now when it continues motion, a little time later, let me draw it in blue. Right? If we draw it a little time later, right, that's the magnetic field. Now the force is in the same direction, right? It's still in the same direction. But what about the torque? What happens to the torque? If you notice over here, the force is pushing it upwards this way. And once it reaches this point, it has momentum, right? It has a certain velocity, angular velocity, and it keeps spinning this way. But if you look, as it's moving this way, the force is now opposite to the rotation, right? So as it moves up, it goes to 0, and then the force stays in the same direction, but because it's on the opposite side of this imaginary, of the circle, of the circular motion over here, now it's over here, the force that's created by the torque, the torque that's created by the force is now in the opposite circular direction, right? So that means that now this torque is going to slow it down, right? So if we just had a DC current over here, right, it'll rotate, right? What will happen is that you'll get a cyclic motion, right? It'll oscillate back and forth. It'll just go back and forth, right? It'll rotate back and forth. Now there's ways to engineer it so that this doesn't happen, right? To make a motor, because what motor you want as soon as you reach this point, then the force switches, right? Then the force goes from this direction to downward, right? You want the force to switch once it passes this point to continue the torque in the same direction. So there's ways to engineer this, right? And one way is to use an AC current, right? That oscillates in sync or in phase with this rotation. So over here on this side, you would have a positive voltage when it's on this side, and then once it rotates and passes this point, the voltage will go negative. And then that would reverse the force, right? Another way to do it is what we do with cars is by using what's called a brushing. And it's just a physical mechanism. So what you have is you'll have this physical device over here, right? And this little semicircular piece of metal is what makes the electrical contact with the wire. So the wire kind of touches this side. Let me just redraw it, right? So that if this is positive and negative, right, as this is rotating on this side, the current will go accordingly like this. And then once it rotates fully around, this side will now be over here, and then the current will reverse itself, and then you'll get torque along the same direction, no matter where this loop is. Right? And we'll finish it up here. I'll go into I'll derive the torque more next time. And I wanted to go into how these motors work, because I think it's actually useful. It's practical knowledge. So, but we'll continue next time. I hope you enjoyed the lecture and gained something out of it. I'll post the answers over the week in the next few days. Let me grade it, and then I'll post the answers. So, sounds good. No. I want to finish this chapter. So next Monday. Let me see. You know what? I'll put up the homework. I'll have it due next Friday. So we're basically done with the chapter. Just like a page left. So I'll post homework 27 for next Friday. Okay. Take care, guys. Stay safe.